Hi everyone, welcome back. So now we're going to be going through Chapter 7 of our Aerodynamics course. And this is, if you're watching the videos from the very beginning, this is now Aerodynamics 2. And I love the name, it's just like some preliminary aspects. What are those? Mostly it's thermodynamics, just kind of covering the basic thermodynamics things that you need to remember to do well in this course. Aerodynamics, we didn't really deal with conservation of energy. Now in Aerodynamics 2, it's really important. So let's jump right in. Okay, so before we dealt with incompressible flow, and now we're dealing with compressible flow. And so what's the big difference here? Well, the difference is that a compressible flow is a very high energy flow. Like, well, how do you know that? Let's look at this car right here. It's going 65 miles per hour. And so I could also say that the air is, the car is stationary and the air is moving over it at 65 miles per hour. And right here, I have a fighter jet. It's moving at 650 miles per hour. So that's a factor of 10 change in the velocity. How about the energy? Well, my kinetic energy of my flow is equal to velocity squared over 2. That's what it's proportional to. Which means that that second flow, even though it's 10 times faster, now has 100 times more energy. Okay, 100 times more energy for the same mass flow rate. And as a note, it would have much different mass flow rate as well, but just based on like the per kilogram energy, it's 100 times more energy. So this is dangerous. For example, if I put my hand out of a car going 65 miles per hour, I can feel quite a bit of air pressure. I put my hand out of a plane moving that quickly, well, I don't have a hand anymore, and most likely the plane's self-destructed and lots of bad things have happened. Don't stick your hand out of a fighter jet, people. Just please do not do that. Okay, so this is the big difference for us. We've gone from a low energy flow to a high energy flow when we go compressible. Okay, now since we're talking about high energy, this means we need to talk about thermodynamics, because thermodynamics is our science of energy. How does it flow? How does it move? How does it change forms? And so we're just going to be covering the basics right here, okay? We'll do some example problems all along the way as we do it. Okay, so first thing, perfect gas. What is this? Well, a gas is just a collection of particles that are in constant random motion. Now, if we have them way too close, like we really compress this, then all those molecules are going to begin to start exerting an electrostatic force on each other. The electrons in one are going to be attracted to the nucleus of another, and repelling the electrons of the other ones. So this would start to affect things. But if they're spaced far enough apart, I can just say, these electrostatic forces are so small that they're negligible. So a perfect gas, which we're going to assume that air is a perfect gas for this semester, is one where I can just say, okay, those spacings between those molecules, they're big enough that I'm not seeing that electrostatic force, and so I can neglect those. And so from that, I'm going to get the ideal gas relation. You've seen it before, either PV equals RT or P equals rho RT. This V right here, that is specific volume, that is not my total volume, just specific volume, per unit mass right there. And so we're going to use this quite often this semester. As for what R is, well, that's my specific gas constant. And this is one thing you should probably write down. It's either 287 joules per kilogram Kelvin or the horrible units of 1,716 foot-pounds per slug degree Rankine. You're going to need those as we go through problems in the future. Just have it memorized better, but just write it written down so you can find it. Okay, so let's try out a quick example right here. So I have an air tank. It has a pressure of 10 atmospheres, great, and a temperature of 300 Kelvin. What is the density of the air in this tank? Well, we can go ahead and use our ideal gas relation to help us out with this. One issue. My specific gas constant kind of tells me what units I need, and if you look in that, I'm not seeing really units of pressure, but don't worry about that. Just know that for any metric problem, just get in the base metric units. So my atmospheres, I need to convert you to pascals, and then things will work out fine. So let's go ahead and convert those units. So first off, 1 atmosphere is 101,325 pascals. Should you memorize that? If you want to, otherwise just write it down. And so I get my pressure is equal to 1,000,000 pascals, which sounds like a lot, and 10 atmospheres is quite a bit, but it's not an insane number. Usually I would do it in kilopascals, but it sounds much less imposing as 1,000 kilopascals. Beyond that, we just plug and chug. So I have my pressure is equal to rho RT, so I just rearrange. And my density is equal to the pressure divided by my specific gas constant and the temperature. Temperature was already in absolute units. We have to have absolute units. And so I can just plug it in. I get that my density will be 11.76 kilograms per meter cubed, which is 10 times the base density of air. Because, air at 1 atmosphere is about 1.176 kilograms per meter cubed. Increase the density, or increase the pressure 10 times, I increase the density 10 times. Okay, so that's a very simple example, but let's keep on going for just a little bit longer. We'll stop after this one. So internal energy and enthalpy. So if we just think about a gas as a collection of like microscopic balls that are bouncing around, well, that's great. That's a great place to start. However, they're not just little balls. Like, they have shapes. They're connected through bonds. If it's, diatomic like nitrogen or oxygen, it looks something like this. But I can also have things that have multiple shapes, like water right here. That'd be 2 hydrogen and oxygen. And so as I add more connections, there's more ways that it can move. And all those motions, translation, rotation, vibration, spin, they all are ways of storing kinetic energy. I can store kinetic energy in this rotation, or in this vibration, or in how much the electrons are translating, or in the spin. All of these things can store kinetic energy. And so they're all important for us. So you're like, okay, well, that's a lot of stuff to take into account. Do I have to really calculate all these vibrations and rotations for every single molecule? The answer is no. We're just going to lump them all together. We're going to call that internal energy, which in this course has the symbol E. If you've taken other courses, a lot of times it's a U, but in this course, lowercase e for internal energy. And if we add in our flow work, we'll get the enthalpy. So that's my pressure times my specific volume. That's more or less the energy it takes to move like a unit of air out of the way, or a unit of some fluid out of the way from the fluid behind it. You use enthalpy if you're flowing, you use internal energy if you're not moving. For us, we're almost always moving, so we're almost always using enthalpy. Okay, so the last little detail here is one more awesome assumption, which is our calorically perfect gas, CPG. That's what it stands for. And that simply means that I can say, okay, yes, technically my specific heats change with temperature, but we're going to assume that they don't change with temperature for most of these problems, because in doing that, I can calculate my internal energy and my enthalpy really easily. Just need to know the temperature and those 2 values for my specific heats. Oh, went too far. And you can find these values in your tables. So I'm going to stop there for now, and next time we'll do a little bit more involved example. Thanks for watching. Hope you're having a good day. See you all soon. Bye-bye.